everyone, welcome back. Today we're going to do a modified Atwood's machine, which is another very common system in the first year physics course. And again, we're going to use a system I already defined earlier. 1, define your system. 2, make a second law equation for your system. And 3, redefine your system in order to find any tensions that you want to find. So here is our modified Atwood's machine. I have mass 1. It is on a table. I will be using friction here. Here is a string. So I'll just label that as tension 1 right now. The string goes over a frictionless massless pulley and is connected to mass 2. Now the idea is right now this is at rest and mass 2 is trying to pull this string and pull mass 1 to the right so it slides toward the end of the table. Now you could be asked a few questions here. Number 1, if someone had their finger on this mass and was holding it at rest, if they lifted their finger, would mass 1 move? In other words, would mass 1 break static friction? Other questions that could be asked: what is the acceleration of the system as mass 1 moves toward the edge of the table? And what is tension 1? I am here to tell you all these questions are answered the same way, and they all use the technique I've been showing you over the last few videos. So to start out, we are going to create our force diagram. So I will start mass 1. We have force Earth on mass 1, which is m1g. We have force upward, force normal on mass 1, which is also m1g because it's a horizontal surface. We also have force friction on mass 1, which is mu times force normal on mass 1, which is mu m1g. We also have tension 1 on mass 1. All right, on mass 2, we have force Earth on mass 2, which is m2g, and we have tension 1 on mass 2. So next up, I'm going to define my system. My system is going to be mass 1, but not the table, the string, but not the pulley, and mass 2. Next up, we will define what direction is positive. Well, in this case, I will define this way as positive. So positive for mass 1 is going to be to the right, and positive for mass 2 is going to be downward. Next up, let's make our second law equation. Acceleration is F net over mass. I have m2g, which is force Earth on mass 2. Tension again is going to cancel. It's negative here and positive here. These two vertical forces also cancel. So the only other force left is minus mu m1g over, how much mass is it pulling? Well, it's pulling mass 1 and it's pulling mass 2. So now you have acceleration in base terms. In order to find our tension, I need to isolate a new system because right now my system takes into account the positive and negative parts of the tension. So my new system is just going to be mass 1. Acceleration of mass 1 is F net on 1 over mass 1, which is going to be, to the right, T1 minus mu m1g over mass 1. Therefore, tension 1 is acceleration mass 1 plus mu m1g. Here's tension 1. Here's my acceleration equation. To show you, if I wanted to use mass 2, I will isolate mass 2 because it also cuts the tension in half. My acceleration equation, acceleration of mass 2, is F net of mass 2 over mass 2, which is m2g minus T1, because it's negative this time, over mass 2. Therefore, T1 equals m2g minus m2 acceleration. And again, find the acceleration for the system. So these accelerations are the same. Once you have the acceleration, then you could solve for anything you're missing here. In fact, the big key is you need to get to this point. Once you make the second law equation, no matter what you are given, there's typically one thing missing you were being asked for. And once you get to this point, it's just algebra. You can find it. Sometimes they will give you the acceleration and they want to know what mu is. Sometimes they give you everything except for mass 2. They know what that is. It doesn't matter. Once you get to this point, then you can solve for whatever is being asked for. You just need to look at what is missing. Okay, so let me use the rest of the screen here to actually show an example this time. Let's say mass 1 is 12 kilograms and mass 2 is 5 kilograms. Mu static is 0.45 5. Mu kinetic is 0.3. Question 1. If mass 1 is held and let go, would this system move at all? Would it break static friction? Now, what that question really comes down to is, would force Earth on 2 be greater than force friction on 1 using the static friction? So I'm going to do F net equals, to the right, I have m2g minus mu m1g. That would be 5 kilograms times 9.8 newtons per kilogram minus 0.45 times 12 kilograms times 9.8 newtons per kilogram. If I do this, I would get negative 3.92 newtons. Now, what does that mean? That means this does not move. This is not actually the net force. What this is telling me is the force of static friction is 3.92 newtons stronger than force Earth on 2, which means the force of static friction is strong enough to not allow this to move. So then what is the actual net force? The actual net force is 0 newtons, because right now static friction is matching m2g. So if you were asked what static friction is right now, it would be equal to this, which would be 49 newtons. It's just that static friction can use more than that if it needed to. So in other words, we just proved that force friction static is larger than force Earth on mass 2. So this system would not move. Okay, let's ask another question. Let's say if someone tapped mass 1, so it started moving, in other words, you forced static friction to be broken, what would the acceleration be, and what would the tension in the string be? So I'm going to use my acceleration here from the upper right-hand corner. So m2g, which is 5 kilograms times, I'm just going to put g, it's 9.8 newtons per kilogram, minus 0.3 this time, times 12 kilograms times g, over 5 kilograms plus 12 kilograms. And I get an acceleration of positive 0.81 meters per second squared. Now, if I got a negative answer, it would be fine. It would just mean that it would be slowing down instead of speeding up. But in this case, since the velocity was tapped to the right, this object would be speeding up. What is the tension in the string? I can use either of these two equations, either this one or this one. You know what? Let's do both just to double check it. T1, I'll use the first equation first. Acceleration, 0.81 meters per second squared times mass 1, which is 12 kilograms, plus 0.3, 12 kilograms times 9.8 newtons per kilogram is 45.0 newtons. Tension 1. I will now use this equation, which is centered on mass 2. Tension 1 is 5 kilograms times 9.8 newtons per kilogram minus 5 kilograms times 0.81 meters per second squared. Rounding to 3 sig figs, I would get 45.0 newtons. So it does not matter which side you use. If you have time to do both, you can check yourself very easily. But these are what is important, making the second law equation, then redefine your system and making another second law equation, because these numbers could have been anything. Once you have this technique down, it doesn't matter what numbers they give you. You can solve for anything you want. All right, I will end this one here. Have a good day. This is Mr. M signing off.